So in the last video, we defined a Turing machine formally. I know that was a lot to take in, and it really does, in order to get used to it, you really just need to see an example. And so today, that's what we're going to do. We're going to show an example of designing a Turing machine to solve a problem. But before we do that, let me just kind of recap the most important parts of the last video for the sake of actually building a Turing machine to solve a problem, which we're going to do in this video. So let's just kind of review. So a Turing machine, remember, as a mathematical object, it's a triplet. It's a collection of three things together. We have a set of symbols, sigma, a set of states, q, and remember the symbols are basically exactly what they sound like. They're the things I'm allowed to print on my scratch paper. My states are my collection of mental states. It's just a bunch of objects that sort of represent where my head can be. And then we've got this thing called the transition function, which is really the meat of the object. It's a function that takes a symbol state pair as an input. Remember, the idea is that I'm staring at a specific part of the page. I'm staring at a specific symbol somewhere on my graph paper, and I'm in a specific mental state. So it takes those two things as an input, and then based on those two things, it's going to produce a three-part output. That three-part output is going to be a new symbol, what I replace the old symbol with, a new state, what I go into as my new mental state, and then a direction, which we're going to index with either -1, 0, or 1. And so that's the syntax, and the idea is that we start with an input, which I wrote here. This might look complicated, but really it's just an input that doesn't involve blanks. So remember, the symbols, in the set of symbols, we're always going to have this special blank symbol. Whoops. The special blank symbol that always kind of acts as an indicator that we're not looking at anything that's been filled in. So the input, we're going to assume, doesn't have any blanks in it. That's what this is saying. So it's sigma minus the blank signal. It's the set of all the symbols except for the blank signal, star. Remember, this clean star operator represents all of the strings in this alphabet. So x, what this says here is just x is a string. X is a string without blanks. So we start with a machine that looks like this. So remember, the visualization, we have graph paper sort of, but we call it tape because it's really just graph paper with a single row, and it's infinite left or right. And the initial state of the machine, given a specific input x, we interpret to be this. So basically, you have your special starting symbol to indicate where my pencil is in the beginning of the computation. And I'm in this initial state q sub I. And following my start symbol is the string x, followed by nothing but blanks. And there's also nothing but blanks over here, too. So it's just blanks to the left, blanks to the right, the starting symbol to indicate where my pencil is, and then to the right of my pencil is the string that's interpreted as the input. And then the transition function defines the steps that my machine takes. So I gave a little example here of just what the transition function tells me to do. So if this is my initial configuration, then here's an instruction. Here's one aspect. We'll have to define the function kind of one at a time, one input at a time. So if delta is defined to be this, so if delta, given the symbol, the start symbol, and the state, the starting state, let's say that it outputs a 5, q3, and -1. Then the interpretation is replace the start symbol with the 5 character, right here. So I've replaced start with 5. I've moved to the left. That's what this -1 means. So I've kind of hopped over to here. And I've transitioned into state q3. So you can see that based on the transition function, I can simulate a step. I can think about a step. And the step takes this configuration to this configuration. That's what delta does. And then I can do that repeatedly. I can think about doing that repeatedly. And so eventually, maybe, we'll transition to a special state in which this Q here is a QH or a QY or a one of my halting states. And at that point, the interpretation is that there's no more steps. The machine halts. And the interpretation is that the computation is over. If I have a QY, then the interpretation is that it's accepted the input. The input is correct. Like the Turing machine says yes to whatever the question is based on this input. If it's a no, then we're rejecting the input. And in the context that we're not solving decision problems, we might instead transition into this QH state. QH just means halt. And in that case, we're usually concerned with a particular string as output. And in that case, whatever we're left with, whatever non-trivial part of the string is there at the end once it's halted, that is interpreted as the output. which we'll read as q as m of x. So m of x is whatever tape configuration we had uh, once we reach a halting state. And technically that output is always defined whether we get qy or qn, but usually when we're talking about qy and qn, accepting and halting states, we don't really care what's on the tape. We just care that we've got an answer. So that's just a little bit of review about what we defined last time, just a quick kind of overview. And today we're going to do an example. Is there anything on this page? No. Okay. So the example I want to solve today is kind of a classic. It's the palindrome problem. So the palindrome problem is really simple. It's the decision problem that is given a string, x, does it read the same backwards? The same backwards and forwards. That's the idea. So for example, dad, that's a palindrome, right? 0, 1, 1, 0, 1 with a 1, 0, 1, 1, 0, 1. That's also a palindrome. It doesn't really matter what the language is, what the alphabet is, and then of course, my name, Alex, that's not a palindrome. You get the idea. Pretty simple problem. We just got to detect whether or not a string is a palindrome. And for the sake of my example, we're going to fix the alphabet as alphabet will be sigma equals, that's the worst sigma I've ever seen in my life. There it is, 0, 1. So we'll have a binary alphabet. And so yeah, let's design a Turing machine that will detect palindromes for me. So let's see. Let's go ahead and think about a palindrome. Let's go ahead and draw an initial configuration for a Turing machine with a palindrome, just so we can stare at it. So here's an initial tape configuration for some input that I'll make sure it is a palindrome. We've got some dots and then a start symbol, and then let's say 1, 0, 1, 1, 0, 1. So this is my initial configuration. Of course, my pencil always starts here at the starting symbol, and I'm always starting in the initial configuration q sub I. And I want to basically do whatever is necessary to stop in a yes or a no state on this input. And so let me go ahead and spell out in English what the idea is going to be, and then we'll try to design a Turing machine that does it. And when I say design a Turing machine, what I mean is essentially define a transition function that will work. And so we kind of have to just run through it. So let's see. So what's step 1 going to be? It's not really even steps. So idea for the algorithm. So to start, we're going to obviously move right. So let's just assume we're already pointed here. So let's say we're pointed here. We're in some state. I'm just going to stay in state qi. Might as well. In fact, let's not even call it qi. You can call the states whatever you want. So I'll call the initial state. Let's actually have a set of the states that we'll fill in. So I already have an alphabet here. So I'm going to define q. I'm going to leave it open, and I'm just going to drop states in here as I need to define them. So we'll start out with a starting state that I'll designate the starting state. I'll call it s. So this will be the initial state. So s will be my initial state. So I'll start in state s. I'll stay in state s when I move right to the next symbol. But I'm looking at a 1. And the idea is that I'm going to remember that I had a 1. remember, so I'm going to say it kind of in general. So look at leftmost symbol, remember what it is, and move right. Move to the rightmost symbol. So that's the idea for the kind of the first, I don't know, step, if you will. I'm going to see this one, I'm going to remember that I had this one, and then I'm going to move all the way to the right and compare. Then the second step is compare. If they don't match, then what's that mean? So let's say I saw one, and then I looked to the right, all the way right. I compared. It's not a one. Then I'm done, right? If this was a zero, clearly this is not a palindrome. So I can just inspect the left and the right. I see that they don't match, and I see that that's not a palindrome. Oops, I don't need that. If they don't match, not a palindrome. Halt and reject. Okay, so that's the idea. Um, Otherwise, we still have a candidate. Otherwise, we still might have a palindrome. So now I know that I do have a palindrome. So what I'm going to do next is move left, move to left, second leftmost symbol. Second leftmost symbol. So I've compared the first and the last. Now I want to compare the second first and the second last. So I go all the way back here. And, whoops. All the way back here. And I look at the zero and I see, okay, it's a zero. And then I move all the way right again, minus the one. Then I see, okay, I keep comparing. And then I just jump back and forth, back and forth, back and forth while burrowing in. And if I get all the way in, then I'm done. And I can say yes. Um, Repeat. And then basically, if we inspect every character without halting and rejecting, then we can accept. At that point, if we just continue in this way, then making it all the way to the end is equivalent to figuring out that the answer is yes. So this is the idea. Now we need to actually uh, define, you know, the actual uh, states or the actual transition function stuff. So I'm actually going to delete all of this now. Sorry. Um, and and we're just going to kind of try to run through that. Okay. Whoops. All right. So first of all, I already did one step. I already drew one step out. Remember, the initial step is right here. I'm in state S, the starting state. I'm pointing at this. So the first thing we've got to define is we've got to say what to do uh, when we're looking at this guy, this play button, and we're in the starting state S. So if we're and obvious, the thing to do is obvious there. So we're looking at this symbol, this state, and then we got to figure out what to do. Well, obviously we're going to want to move right. That's the last kind of the triple. We're going to want to replace this with something. But in fact, I'm actually just going to replace it with itself. I'm not going to do anything to it. And then I'm going to move it. I'm actually going to even stay in state S, I think. And I'm going to move right. So this tells me that in the first step of the algorithm, all I'm going to do is move right, and I'm still in state S. So I'm looking at this. What do I want to do after that? Well, if I'm looking at a one, I'm in state S. Remember, I want to remember that I was in state one. Sorry, I want to remember somehow that I had a one here. So how do I do that? Well, I write a state for it. I'll call it Q1. So I kind of move into state Q1, And then just knowing being in state Q1 tells me that I had a 1. So, I mean, my mental state kind of changes to reflect that I had seen a 1. And I'm also obviously going to move right. And what do I want to do with this 1? Well, remember, eventually I'm going to move backwards. I'm going to move back to the left, assuming that there's a 1 over here. And so I want to be able to kind of remember that I've seen this already. So I'm just going to delete it, actually. I'm going to replace it with another start symbol. And you'll see why that is. But the bottom line is I want to remember that I've looked at this, and there's no reason to keep it after I've looked at it once. So I'm gonna replace it with a start symbol so that I can kind of, when I'm moving back, I know where to start. I know where to stop, I mean. And just like that, you'll see that in order to get to this 1 over here, I'm gonna have to realize that there's a blank following it. So now what I want to do is I've seen this 1, I remembered that I'm in a 1 state, and what I want to do is I just want to move right until I get to a blank, and then I'm going to double back. So until seeing a blank, then move back. 1. That's the idea. So how do we do that? How do we just kind of go into this almost this while loop that takes us all the way to a blank? Well, um, let's just go ahead and think about it. So does it matter what I see until I see a blank? No, it doesn't. And I don't want to delete anything either. So let's just pretend, let's just write, let's look at the 0. Suppose I see a 0, and I'm in state Q1. Well, then what do I want to do? I want to leave it alone. So if it was a 0, I replace it with a 0. That is, don't do anything to it. And I also want to stay in state Q1, and I want to keep going right. And if I'm in state 1, and I'm looking at Q1, then I, again, want to leave it alone. And I want to stay in Q1, and I want to keep moving right. So these two commands here will just continually move me right without doing anything while remaining in state Q1. That is the state that remembers that I saw 1 as this symbol. And then finally, when I see a starting symbol, or sorry, when I see a blank, excuse me, then I want to remember that I've seen a blank. So I want to remember that I've seen a 1, but I also want to um, uh, I also kind of need to real my mental state has changed, right? So I need 2 mental states that both involve remembering that I've seen a 1. So I'm actually going to have a Q1. I'm also going to have a Q1, let's say prime. So I want if I see a blank and I'm in state Q1, that is the state that says my mental state. So my mental state from Q1 basically says I've seen a 1 and I am moving right until I get to a blank. Now I've gotten to a blank. The mental state changes a little bit, but I still need to remember that I've seen a 1. And I obviously don't want to replace the blank with anything, so I'm going to leave that alone. Replace the blank with a blank. Remain in state Q1, but also need to double back. So I'm going to go into state Q1 prime, and then I'm going to move left. So I put a -1 there. So I've basically what's going to happen. So given these 3 inputs here, so given these 3 commands for delta, both these 3 involving Q1, what's going to happen is I'm going to replace this 1 with a start symbol, and then I'm going to move like this. That's going to be I'm going to stay in state Q1 the whole time, and then I'm going to double back. Hopefully that makes some sense. So now I'm here. Now I'm pointed at this guy, and I'm in state Q1 prime. And before we go any further, I should probably make sure to point out that obviously we need an equivalent situation to these 4 symbols, but for Q0. Um, so need also similar commands for a 0. In fact, let's go ahead and just write those down just to have them. So kind of analogous to that. So let's suppose that we, instead of seeing a 1 here, which we initially did, now it's a triangle. If it was a 0 instead, what's going to happen? Well, if we see a 0 and we're in the starting state, I obviously need to do the same thing, replace it with a triangle, go into state Q0 now, and then go right. That would be the equivalent to this command, but for 0. For this one, if I see a 0 and I'm in state Q0, then that means I'm moving right. Remember, I'm moving right, I see a 0, I don't want to do anything. So going to leave it alone, going to stay in Q0, I'm going to move right again. Same thing with a 1. Whoops. And then finally, I keep doing that until I reach a blank. Whoops. It's a blank, and I'm in state Q0. I want to replace it with a blank. I want to go into state Q0 prime, and I go -1. So now I've got kind of an equivalent thing that says, remember the symbol that I saw here, move all the way until you see a blank, and then double back, still remembering what you saw before. So I'm also going to go ahead and... So I'm kind of adding states as I need to here, as you can see. And I think I'm only going to need one more. But now, okay, so now now we need to compare. Now we're at the crucial moment. So now there was a 1 here. I'm in state Q1, and I see a 1. So what do we want to do? Let's see. So so obviously the string I wrote down was a palindrome. This was a 1 originally. And so I shouldn't halt here, and indeed I won't. If I see a 1 and I'm in state Q1 prime, then I'm going to not halt. And since I'm going to want to repeat the process, since I'm going to want to eventually go, I'm going to want to go back to this 0 now, and now search again in the same manner to find the rightmost thing. So I'm done with this one. And so just like I replaced the original one with a triangle here, I'm going to replace this one with a blank. I'm going to erase it. And I'm going to go into a new state. I'll call it B for back, I guess, which I will add to my list of, oh God, which I will add to my list of states. And I think I'll close it there. I don't think I need any more states. And I will go back 1. Okay, so what I've done now is I don't halt. Oh, and by the way, let's add the other thing to do. So if I see a 0, then what do? If I see a 0, then that means that the number that they don't match, right? If I see is if I had a 1 here, and then I look at a 0 here, then they don't match. So I want to halt in a no state. So the command should be, it doesn't really matter what I do. I guess I'll erase it just for kind of symmetry. But then I want to go into a Q no, and I'll put a 0 here just to say don't move. Doesn't really matter what this or this is. The important part is that I'm halting. In fact, I might even circle that as like, this is a crucial moment. Okay. What else could this be? Well, let's not go there yet. So now what's going to happen? Well, I'm going to erase this guy. That's what I just said to do, and replace it with a blank or halt. But since this is a palindrome, that's what's going to happen. And now I want to double back until I see a triangle again, and then jump forward. And that's why I had the back state. So what's going to happen is I'm going to have, I guess I'll continue up here. So delta of, really I'm going to need to, so if I see a 0 and I'm in the back state, then I'm going to leave it alone, obviously. I don't want to delete it, so I'm going to just replace the 0 with a 0. I want to stay in my going back state, and I want to say -1 here. So that's going to move me back. Same thing for 1. Leave it alone. Continue moving back. And then continue doing that until I get to a start symbol. And you can see I'm using this start symbol. This start symbol is useful for various things. You can do whatever you want with it. So I'm going to move back until I see a start symbol. And then I basically want to repeat the process. So at that point, I want to leave it alone. And then I think I'm going to just recycle my S state. Because at that point, it's like the program repeated, right? That was the point of replacing the first symbol with a start symbol and the last symbol with a blank. By replacing the first symbol with a start symbol and the last symbol with a blank, I can just pretend the whole program starts over. So now I can actually go into state S again. I can just pretend the program's repeated, provided I move right forward 1. So that's what's going to happen next. I'm going to move all the way back here until I see this guy, and then I'm going to jump forward again. And then at that point, I'll be in state S, and I'll be looking at a 0, and now I'm looking at this new string. I just kind of repeat the palindrome problem again. And so you can see that's going to repeat itself. I need to add a few more commands for delta. That's going to repeat itself until everything's blank. So let's just kind of think through the process. What's going to happen now? Well, I've already got I've listed my equivalent 0 stuff over here, right? That's what these guys are going to do. So based on these 4 guys, I'm going to erase this, replace it with a start symbol, and I'm going to move over here in state Q0, and then it's just going to keep going. I'm going to move over here, and then I'm double back, and at that point, I'll be looking at Q0 in a 0 state, so I'll be in Q0 prime, and then I compare it. Did I define those? No, I didn't. I didn't define the prime states for 0, so let me write those down. So if I'm in state Q0 prime and I'm looking at a 0, then I want to delete it, just like I did over here, and then I want to go into my back state again, and I want to go back 1. Delta 1, Q0 prime. That would be again another halting state in which I stop, right? I was looking at a 0, now I'm looking at a 1, so they don't match, so I want to halt. Halt at that point. Halt and reject. There's another rejection state. And then finally, that's going to take me into my back state. And so what's going to happen then? So at that point, I'm just going to erase this, replace it with a U. Then I'm going to move back here until I see this, jump forward again. And then I'm going to delete this, place it with a start symbol, jump forward to this, and then double back to here. And then I'll be in Q1 prime, and then I'll check, and apparently it works out, so I delete it, replace it with this thing. Whoops. And now I'm at the empty string. So what's going to happen then? Well, let's just see. Well, now I double back to here. So I'm going to be in my back state at that point. And that back state is going to, I'll be at a back state, and I'll be looking at this. So I'll go into my start state again. And so what's going to happen is I will be pointed right here in state S. So basically what this is going to look like is it's going to be as if I didn't input a string at all. It's going to be as if I inputted the empty string. And the question we need to ask is, did I actually? No, I did not. So, I mean, what needs to happen at that point? Well, if I'm looking at a blank, technically the blank string is a palindrome, right? So technically, blank string is a palindrome. And so I'm going to accept. Right? And that's that, I think. I think I'm forgetting like one thing. So that was an even, well, I can't remember anymore. Let me see. 1, 2, 3, 4, 5, 6. Yeah, that was an even number of characters. If I get to an odd number of characters, then I think I'm going to end up in a situation where I had one character here. Let's just think about that lastly. So let's just say I inputted a 1. Let's say that was the input, a single character string. Well, single character strings are also technically palindromes. So let's make sure my program works to cover with that too. So let's see. So I see a 1. So at this point, I'm going to be in state S, staring at a 1. And so that's going to take me into state Q1. Replace this with a blank. Or sorry, no, that's going to replace this with a oops. Going to replace this with a triangle actually. It's going to take me into state Q1, and it's going to point me right here. And then it's going to double back. And so what's going to end up happening is that I'm going to be in state Q1 prime, staring at a triangle. Now, do I have an instruction for that? I do not. I don't. So that I need to add. So finally, so if I'm in state Q1 prime and I'm staring at a triangle, then that means that I was looking at a one character string, or at least I was in a point of the program where it was as if I was looking at a one character string, in which case I want to say yes. So I replace it with whatever, I'll just replace it with itself, and then go into a Q yes state, and that's that. And then I want the equivalent thing for a 0. So same thing, if it was a 0 there, I would have been a Q0 prime state, looking at a triangle. I again want to do nothing, I guess, go into a yes state, and it doesn't matter where I move. And so there it is. I think that's all the commands that I need. I think I've actually defined everything. So it's ugly, but this technically, this is a definition of the transition function, and that defines the whole Turing machine. Let's go ahead and think about this for a second. So the transition function, right, is a function that takes a symbol state pair and returns an output. Now, how many symbol state pairs are there? Well, how many symbols do I have? 4, technically, right? I have 0, 1, but then I also have, my blank symbol and my start symbol. How many, and then how many states do I have? 1, 2, 3, 4, 5, 6. So I have 6 states, 4 symbols, so that should be 24 possible inputs. How many definitions of transition functions have I given here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there's some I haven't done. And I think it's pretty safe to assume that I'm just never going to go into those states. Um, you know, technically there's a little proof to do there to say that, given a partially defined transition function like what I defined here, you can always extend it to a new transition function. But I mean, just think about it kind of as a programmer. Those symbol state pairs are never going to be encountered. For example, if I'm in state Q, I think, I don't know. I've got three backstates. Okay, yeah, there's an example. So for example, I'm never going to see a blank while I'm in a backstate. If that happens, then something went wrong. And that's why I haven't defined it here. So you can define it to be whatever you want. So there's technically a few transition functions outputs left to define to have a fully defined transition function, but there is a theorem that says you can always extend it to something that's consistent or has nice properties. So this is enough to define the whole program. So technically there's a couple more things to define, but this is the full palindrome program. This will do what I described in English before. So hopefully that helps. That's an example of building a Turing machine. I've got a collection of symbols, I've got a collection of states, and then most importantly, I've got the program. So that's just a little example of a simple Turing machine to solve a specific problem.